something remarkable happened in the world of artificial intelligence, and it challenges everything we thought we knew about how powerful AI needs to be. Google released Gemma 4, a free, locally runnable artificial intelligence model that performs better than competitors 20 times its size. This isn't a marginal improvement or a niche achievement. This is a fundamental shift in how AI development works. And the implications ripple far beyond Silicon Valley laboratories and research institutions. For years, the narrative around artificial intelligence has been simple. Bigger is better. OpenAI built GPT-4, a massive proprietary model accessible only through expensive API calls or premium subscriptions. Anthropic developed Claude, requiring users to pay for access to frontier-level capabilities. Meta released its open-source models, but they still demanded substantial computational resources. The assumption became embedded in the industry consciousness that reaching cutting-edge performance required increasingly enormous models, higher cloud computing costs, and dependency on centralized services controlled by tech giants. Then Google made a different choice. Rather than racing to build the largest model possible, they engineered something more intelligent, a system that accomplishes more with less. Gemma 4 represents a dramatic departure from this arms race mentality. The model is substantially smaller, requiring far fewer computational resources, yet when measured against industry standard benchmarks, it outperforms models exponentially larger. Tests using Arena AI, AIME 2026, and Live Code Bench consistently demonstrate that Gemma 4 achieves superior results compared to models claiming 20 times its parameter count. The technical architecture behind this achievement centers on mixture of experts design, which functions like a smart routing system for artificial intelligence. Rather than activating every computational pathway for every task, the model learns to identify which components are necessary for specific problems. This selective activation means that inference happens faster, memory consumption drops dramatically, and the system becomes practical for devices beyond data center servers. Available in 31 billion and 26 billion parameter variants, Gemma 4 can run directly on laptops, local machines, and consumer-grade hardware. What makes this genuinely transformative is the ecosystem implication. For the first time, developers, students, researchers, and organizations operating under genuine privacy constraints can access frontier-level artificial intelligence without paying subscription fees, without uploading sensitive data to cloud infrastructure controlled by distant corporations, and without dependency on rate-limited APIs that can refuse service or increase prices without notice. The model runs offline, entirely on local hardware. Your data stays on your machine. Your inference costs nothing. Your processing speed depends only on your device's capabilities, not on server queue times. This represents a profound democratization of AI access. Consider the developer in Lagos building an AI-powered application for African markets. Consider the student in a developing economy wanting to learn machine learning without purchasing expensive cloud credits. Consider the healthcare organization managing patient records under strict privacy regulations that forbid cloud storage. Consider the researcher exploring edge deployment scenarios where devices must operate without internet connectivity. For all these scenarios, Gemma 4 doesn't just offer an option, it opens possibilities that were previously sealed behind paywalls. Google's strategy becomes clearer when you understand the long game. By releasing Gemma 4 freely, Google isn't abandoning monetization, they're shifting it. They're building an ecosystem where developers choose Gemma because it works brilliantly on local hardware, creating loyalty and mindshare before those developers potentially scale to cloud-based Gemini infrastructure. They're validating their technical capabilities and demonstrating that Google can compete effectively in open source AI, not just proprietary systems. They're expanding the talent pool of developers comfortable with Google's AI frameworks and tooling. The traditional AI providers face a genuine dilemma. OpenAI cannot easily match Gemma's local-first free-tier strategy without undermining their premium subscription model. Anthropic faces similar constraints. Meta's open models, while free, haven't achieved the same efficiency benchmarks or market penetration. The landscape is shifting, and smaller, smarter models are becoming the new frontier. Before we continue exploring the technical details and market implications of this shift, I'd like to ask you something. Subscribe to the channel and tell us in the comments where you're watching from. This story connects directly to AI accessibility in your region, and we'd love to hear your perspective as we dive deeper into what this means for developers, organizations, and anyone building with artificial intelligence. The technical architecture powering Gemma 4 reveals why conventional thinking about model size has become obsolete. At its foundation sits mixture of experts technology, a design philosophy that fundamentally reimagines how neural networks process information. Rather than forcing every computational layer to engage with every input, MOE systems function as intelligent routers, activating only the specialized pathways necessary for each specific task. Imagine a hospital where physicians don't all examine every patient. Instead, a triage system directs each case to the relevant specialist. That's essentially how Gemma 4 operates at scale. This architectural efficiency translates directly into measurable advantages across multiple dimensions. The 31 billion and 26 billion parameter variants achieve inference speeds that larger models cannot match on equivalent hardware. When tested against competitors operating with 10 to 20 times more parameters, Gemma 4 consistently delivers superior responses on reasoning tasks, coding challenges, and domain-specific problems measured by Arena AI leaderboards, AME 2026 competition benchmarks, and live code bench metrics. The performance gap isn't marginal, it's decisive, suggesting that raw parameter count has become a crude proxy for capability, misleading developers into overbuilding systems that waste computational resources. Memory requirements present another critical advantage. Larger models demand specialized GPUs with substantial VRAM, pushing entry costs into thousands or tens of thousands of dollars. Gemma 4 runs effectively on consumer hardware available at ordinary retail prices. A developer with a laptop featuring 16 gigabytes of RAM can execute Gemma 4 inference without noticeable system slowdown. This isn't just a feature, it's a complete inversion of the traditional accessibility barrier. Organizations no longer face binary choices between cloud dependency or abandoning AI capabilities entirely. The multimodal capabilities integrated into certain Gemma 4 variants extend functionality beyond text processing. Vision integration allows the model to analyze images, diagrams, and visual documents, enabling applications from document processing to accessibility tools. These capabilities appear without the explosive parameter bloat typical of earlier multimodal attempts, suggesting that efficiency improvements apply across domains, not merely text-based tasks. Local inference represents the transformative advantage for privacy-conscious deployments. When a model runs entirely on user hardware, data never traverses networks to distant servers. Healthcare applications handling protected patient information can now deploy AI without regulatory friction. Legal firms processing confidential documents achieve compliance without uploading sensitive materials to third-party infrastructure. Financial institutions managing proprietary trading algorithms avoid exposing competitive advantages to cloud providers. This privacy-first capability becomes particularly valuable in regulated industries where data residency requirements would previously have eliminated AI adoption entirely. The absence of API rate limits changes development patterns fundamentally. Cloud-based models enforce request throttling, creating bottlenecks for developers building high-volume applications. Gemma 4 deployed locally eliminates these constraints. A startup processing thousands of documents daily no longer calculates per-request costs or designs around rate limit architecture. Processing capacity becomes limited only by available hardware, not by subscription tier or commercial terms that providers can modify unilaterally. Offline operation addresses scenarios traditional cloud models cannot serve. Applications deployed on aircraft, ships, or remote locations without reliable internet connectivity become feasible. Edge devices including mobile phones, IoT sensors, and embedded systems can now execute frontier-level reasoning without network connectivity. This capability fundamentally expands where AI computation becomes possible. Comparison matrices reveal Gemma 4's positioning across established metrics. Against GPT-3, the efficiency ratio favors Gemma 4 dramatically, superior performance at a fraction of the computational cost and zero subscription expense. Against Claude 3 Haiku, benchmarks show competitive or superior reasoning capabilities with identical local first advantages. Against other open models, Gemma 4 distinguishes itself through the efficiency gains that make the entire category viable. Transparent acknowledgement of limitation strengthens credibility. Gemma 4 operates within specific token windows that constrain context length for certain applications. Particular task categories, highly specialized domain knowledge requiring massive external databases may still demand larger models. Specific safety and alignment behaviors reflect different design priorities than competing systems. These constraints represent genuine engineering decisions, not deficiencies. capabilities, and they inform realistic deployment decisions. The practical implication crystallizes into a single observation: efficiency itself has become the competitive advantage. No longer does more powerful mean larger. As the implications of Gemma 4's efficiency ripple outward, the broader market begins its inevitable transformation. The narrative that larger models automatically deliver superior results has become demonstrably false, and this shift carries consequences extending far beyond benchmark comparisons or technical specifications. Organizations built on the premise that proprietary scale equals competitive advantage now face strategic recalculation. The bigger is better philosophy that justified premium pricing and API consumption model suddenly appears antiquated. Market disruption accelerates through multiple channels simultaneously. Developers who previously accepted cloud dependency as inevitable now evaluate local alternatives with genuine viability. Startups no longer need venture capital specifically allocated for API costs and infrastructure expenses. The barrier to entry that once required significant funding simply evaporates. A student in a developing nation with limited cloud access can now build AI-powered applications matching the sophistication of well-funded teams and technology hubs. This democratization represents more than cost reduction. It fundamentally reshapes who can participate in frontier AI development. The beneficiaries extend across multiple constituencies. Developers targeting cost-sensitive products gain access to capabilities previously reserved for well-capitalized organizations. Students learning machine learning no longer practice against crippled models or free-tier limitations that frustrate hands-on understanding. Organizations prioritizing data privacy discover that efficiency and confidentiality align perfectly rather than existing in tension. Governments concerned with technological sovereignty and data protection find pathways toward AI adoption without external dependencies. Emerging markets operating with constrained infrastructure investments suddenly access capabilities that wealthy nations took for granted. Google's strategic calculus underlying this release deserves careful examination. Providing sophisticated AI models without direct monetization appears counterintuitive until examining the ecosystem logic underneath. By establishing Gemma 4 as the standard that developers learn, integrate, and build upon, Google positions its entire platform ecosystem as the natural infrastructure layer. Developers proficient with Gemma 4 eventually deploy applications requiring additional services, storage, databases, compute scaling, security infrastructure that Google's cloud services naturally provide. The free model functions as ecosystem entry point rather than revenue terminator. This approach validates Google's broader Gemini infrastructure investments, while simultaneously expanding the talent pool of developers comfortable with Google's frameworks and philosophies. Competitors offering expensive proprietary solutions now compete against free alternatives that demonstrate superior efficiency metrics. The long-term advantage accrues to whichever company successfully owns the developer mindshare and platform preference during this transition period. Google's timing positions the company advantageously, though the strategic response from competitors will prove equally instructive. The broader shift toward efficient open AI models accelerates across the industry ecosystem. Other organizations releasing models increasingly emphasize optimization and local deployment rather than raw parameter counts. The race toward trillion parameter models has decelerated noticeably as efficiency gains demonstrate superior practical value. Research institutions previously pursuing scale-focused strategies refocus on architecture innovation and algorithmic improvements that deliver capabilities without proportional computational inflation. Societal implications extend into governance and policy domains. Reduced vendor lock-in creates genuine competitive pluralism rather than the concentration characterizing earlier AI development. Privacy by default becomes a competitive advantage rather than a compromise, potentially reshaping how organizations approach data handling. The concentration of AI capabilities among a handful of cloud providers begins decentralizing toward edge devices and local infrastructure. Communities can now deploy AI-powered services without external dependency or surveillance concerns. The sustainability dimension warrants attention. Smaller models consuming less electricity directly reduce environmental footprint compared to enormous systems requiring specialized cooling infrastructure and substantial power consumption. As climate concerns increasingly influence technology adoption decisions, efficiency becomes morally compelling alongside economic advantage. Future developments will reveal how completely this transition proceeds. The expected adoption trajectory includes widespread integration into open source projects, enterprise environments deploying local instances for sensitive workloads, and edge devices executing previously impossible computational tasks. Long-term questions persist. How will providers sustain development funding for free models? How will competitive responses from OpenAI, Anthropic, and Meta reshape the market? Will efficiency gains continue accelerating, or will we encounter diminishing returns? One certainty remains unambiguous: the announcement of a free, locally runnable model outperforming systems 20 times larger marks a definitive inflection point. The era of exclusive, expensive, centralized artificial intelligence has reached its conclusion. What emerges instead is fundamentally more distributed, accessible, and aligned with the capabilities of individuals and communities rather than institutions controlling vast computational resources. This transformation only accelerates from here.